Hello, my name is Samuel Schmidtke, and this work is on self-constructing neural networks through random mutation. So the inspiration for this work comes from the idea of self-construction in nature, particularly of the biological brain. Biological brains employ a strategy for self-construction which combines both genetic factors and experience-dependent changes that take place over the course of a single continuous lifetime. A famous example of this is shown in the image on the right, where a cat was blindfolded in one or both of its eyes, and the brain regions that correspond to visual processing in that eye developed structurally different based on experience. And that may sound trivial, but current neural architecture search methods are often not equipped for such essential capabilities, namely intra-lifetime neural development. These methods are typically dependent on rolling out multiple agent lifetimes, where the same exact conditions are repeated for millions of time steps, with little novelty. Now, one thing I want to point out is not all neural architectures are created equal. Rather intuitively, some neural architectures work much better for certain tasks than others. So much so that a significant amount of research effort in the past decade, and even today, has gone into designing neural architectures that are suited for specific tasks. In response to this, people have been slowly realizing that instead of designing neural architectures manually, instead we can actually learn them in the same manner we're learning the weights. One of my favorite works that took this to the extreme to really show how important neural architecture was in any given task is by Adam Gair and David Hawes' work on weight-agnostic neural networks. Basically what they did is they showed if you only learn the architecture of a neural network and evaluate the performance of that network using random shared weights, you can evolve networks capable of solving several different tasks with architecture alone. Now, the idea proposed in this work is a simple algorithm for neural architecture search called random mutation search. Just as the name suggests, the algorithm works by accepting or rejecting random mutations based on experience. The algorithm starts out with just input and output neurons with no connections between them. The network is then randomly mutated using one of the four mutations at the bottom. There's add neuron, add connection, change activation function, and remove connection. The performance of the network is evaluated over a specified time interval, or in the case of episodic learning, an episode. And if the performance over that interval is greater than the previously accepted mutation, starting out at 0, then it is accepted into the structure. You might be thinking this is very reminiscent of genetic algorithm, namely NEAT. However, the key difference is that the population size in this is adaptive and adjusts based on how locally optimal solutions are. There's an additional mutation that's not a core part of the algorithm, but we use it in this work, and that is the weight change mutation. So to optimize weights, instead of backpropagation or local learning, the weight values are randomly mutated by selecting a connection randomly and sampling a value from a discrete set between -1 and 1. And this was just all done to keep the algorithm as simple as possible. Also in practice, the mutation acceptance threshold is also adaptive to account for variance. There's a bit of decay there, and all that's described more in depth in the paper. Okay, so the performance of random mutation search was compared with neuroevolution of augmenting topologies, NEAT, evolutionary strategies, and proximal policy optimization. Out of the three of these, NEAT was the most direct comparison to random mutation search, since NEAT also optimizes neural topology with random mutations. However, this is done with large populations of neural networks using genetic algorithms. Random mutation search, on the other hand, just uses a single parent and has an adaptive population size based on once it's found a better performing topology. So here we see that random mutation search only outperformed the other optimization methods on the ant locomotion task. However, it remained relatively competitive with the three algorithms on the other two tasks. The ant locomotion and swimmer task reward velocity away from the initial position in any direction, and the swing up pendulum rewards balancing the pendulum in the upright position, as well as a small penalty for movement. Keep in mind that the weight optimizations are also taking place through random mutations, and the performance of random mutation search could be significantly improved by adding backpropagation or local learning. So one of the more interesting pieces of work we did was to showcase the lifelong learning capability of random mutation search. We started out with the quadrupedal locomotion model from Majoko's ant, and we modified this to allow morphological randomizations, as you can see in the two bottom images, and limb impairment at the top there. These modifications occurred randomly over the lifetime of the walker. This was to allow for a non-repetitive environment, so we could have lifelong learning, in addition to the lifelong learning environment having no environment resets. And as a consequence of this, if the quadruped were to make a mistake, like flipping onto its back, it would have to learn to correct itself all on its own. As in, the typical ant environment would re-flip it back onto its back, or onto its front. One of the interesting set of observations from the network composition of the produced networks from random mutation search is that on the locomotion task, there were 95% less connections developed than the fully connected architecture, and 28% less than what was produced by NEAT. It was also noticed that as the task complexity increased, so does the number of connections in the network. As you can see in the table, going from the locomotion only task to the lifelong learning setting almost doubles the total number of connections in the network. And this was relatively consistent with repeated experiments. However, the types of connections, whether it be feed-forward, feedback, or self-recurrent, remain relatively consistent across increases in connections. And descriptions of, if you're not familiar what those are also in the paper. So here I want to talk about some of the limitations of the algorithm. I'll play this video here. So the solutions, as you can see on the right, are often very greedy. So this was a suboptimal greedy solution with a relatively bad set of hyperparameters, where the network only connected to a single limb, and it's kind of like inching itself along with that single limb, and none of the other limbs are actually contributing anything. Another limitation is that, specifically in this work, weight optimizations were done through random mutation, and further work might improve this algorithm by combining that with gradient methods or local learning. Another limitation is, as the network size grows, the probability of connecting to any individual neuron decreases. Rather, it might be more beneficial to have each neuron deciding who it connects to, so that when a new neuron is added, it doesn't become sparser and sparser and less likely to be connected to. And a final one is that it would be inefficient for large state action, state input and action output. So if you had like an image, for example, it might not work very well with that, which is the same problem that NEAT has, and it's not surprising that this algorithm inherited that issue. Well, otherwise, thank you for listening, and I hope you learned something. See ya.